All right. Good evening, everybody, and welcome to today's technical lecture titled Flow Assurance Challenges in Deep Water Operations, a case study of the Gulf of the Guinea Niger Delta Basin. My name is Ose Aisiku, and I am your moderator for today. Um, Running through the agenda of today, we'll be beginning with the opening prayer, and then we would have a safety briefing by Mr. Israel Chibike, the opening remarks by Dr. Luashin Adetona, the introduction of the guest speaker, and then the lecture proper. We'll also have an interactive Q&A session later and key takeaways from the presentation. We'll have the photography, the vote of thanks, and that will bring this technical lecture to an end. So, without much further ado, we'll begin with the opening prayer, which I will read out, and everyone can unmute and say amen afterwards. All right. O God of all creation, grant this our one request. Help us to build a nation where no man is oppressed, and so with peace and plenty, Nigeria may be blessed. And we can unmute now and say amen, and also to confirm that you
Amen.
can hear me.
Amen.
All right. All
Amen.
right. So we'll have our safety moment now by Mr. Israel Chibike. Please, if you're on the call, you can unmute and have the floor.
All right, thank you, moderator, and good evening once again to everyone, ladies and gentlemen. Once again, I want to welcome everyone to another edition of our monthly technical session. And just as is our practice in the industry, we would like to take a moment to observe safety. All right. So
Next
first
slide,
off,
Ose.
okay, thank you. So as we all know, once you join a meeting like this, you are expected to mute your mic when not speaking. And if you have any reason to speak, or if you want to be heard, if you want to be given the floor, please you can indicate by using the raise of hand gesture. And if you have any comments or question, you can do that. You can do that in the chat box using the C command for comments and the Q key for questions. And also, if you're making use of a headset, ensure you can hear the safety alarm from your end to avoid any sort of inconveniences or in case of any emergencies. And always be at alert, observe your environment, be conscious of your environment, or even while on the call. Always stay safe and maintain a very good sitting posture to avoid health inconveniences during or after the call. These are the few safety things that we have to observe. All right. So do well to enjoy the rest of the session. Thank you.
Thank you very much for that safety moment. And I do hope that we're all able to follow through with the safety precautions as we proceed. Next on the agenda is the opening remark by our section chairman, Dr. Luashi Adetona. Section chairman, sir.
Good afternoon. So, where's the basement?
Good evening, everybody. Can you hear me?
Yes, sir, loud and clear.
All right. This is another eventful technical session, and we are privileged to have Engineer Dr. Oluwadero on the call with us. It's an honor to have him as one of our technical presenters. I want to appeal for everyone already on the call. Please, this is one of the rare opportunity where you hear technical professionalism coming into play in the sense of flow assurance. Please, for every student, young professional that hopes to be involved in flow assurance, this is an opportunity and eye opener. Get your pens, get your things ready to learn. And for some of the student chapter president I'm seeing on the call, kindly put it on your general platform. Let your people join now. I'm not seeing PTI especially being represented yet. I'm not seeing FUPRI being represented yet. And I'm not seeing most of my young professional joining, let's assume is because of movement, rain, and the rest. So I believe in the next 5-10 minutes before the presenter will go in details, a lot of us would have joined to learn for this August presentation. This is not just a lecture. This is not just a teaching. This is actually a technical presentation with right perspective to delve more into flow assurance for all. So please, let us welcome Engineer Dr. Oluwadero as he comes in for his presentation. Moderator, thank you, and please everybody have a wonderful time out as we proceed with the presentation. Thank you.
Thank you very much, sir, for that. And like our section chairman has said, let us all get ready for this session. Get your pen, your paper, whatever notepad you're using to take notes, and get ready. So our guest for today is Engineer Timothy Ayodeji Oluwadero. He is a petroleum and mining engineer, a researcher, and a technical trainer with expertise in flow assurance, multi-phase transport, corrosion engineering, and damage mechanisms in oil and gas facilities. He serves as Deputy Chief Officer in training in the Department of Petroleum Engineering and Geoscience at the Petroleum Training Institute, Efron, Nigeria, where he delivers specialized technical training for professionals across the petroleum industry. He holds an MSc in Petroleum Engineering from the University of Ibadan and a postgraduate diploma in Flow Assurance from the University of Aberdeen, United Kingdom. He also has foundational training in mining engineering from the Federal University of Technology, Akure, providing additional expertise in particle transport and solids handling in petroleum production systems. Engineer Oluwadero's research focuses on experimental hydrodynamics, industrial mixing, corrosion, and materials degradation in energy systems, including peer-reviewed publications in engineering and scientific journals. He is a registered engineer with the Council for the Regulation of Engineering in Nigeria and a member of the Society of Petroleum Engineers, Nigerian Society of Engineers, Association for Materials Protection and Performance, and the Council of Nigerian Mining Engineers and Geoscientists. Ladies and gentlemen, let us give it up for our guests and special speaker for today. You have the floor now, sir. Welcome.
Thank you so very much, Ose. I was almost pronouncing the name as Oshe, but when you mentioned it, I quickly picked the correct way to pronounce the name. I want to especially thank the section chair and the person of Engineer Dr. Adetono. This is a very, very big privilege, speaking to professionals as well as intellectuals across board, whether students or already practicing. So it's my privilege it's a very, very big honor to me to be able to be the guest speaker for this technical lecture edition. So if I have my way now, can I go ahead and share my slide? Hello?
Yes, you can. Okay. I'll just stop sharing now.
Okay. Oh, okay. It's also disabled participants screen sharing. So can you help me to rectify that?
Okay. Mr. Bashir?
Okay, Madam Chelsea, kindly assist, make the guest presenter to be a host, please. Thank you.
So while we wait for that to be done, today I just want to take this time out to speak on the flow assurance challenges in deep water operations. And we'll be looking at, especially we'll be narrowing down to Gulf of Guinea, and more importantly, the part of the Gulf of Guinea that concerns us. why this particular topic? Why is it important? I know currently Nigeria is actually rooting for production quotas of about 2.4 million barrel per day to about 3 million barrel per day. And currently we are averaging between 1.5, sometimes below, sometimes a little bit above. That's without condensates. One of the key challenges that, can I go ahead and share now? Okay, see who's disabled participant. So one of the key challenges to that effect is because basically Nigeria focus predominantly on offshore production in the time past. And in the recent time, we begin to hear about
Engineer
disinvestment.
Timothy, sir.
Yes.
Check your chat. Can you just share your presentation slide via WhatsApp so that we can pause a project?
Okay. Okay, let me just do that now. So I've sent it to the share, right?
Yeah.
Okay. 1 minute, please. So on the way. Just 1 more minute to be there. It's loading. Oh, okay. Send it to, let me store your number. I sent it to the share before. Let me store your number, Bashir. I just saw that private message. 1 minute, please. Three. Oh. Okay. So it's already with the share, section share. I don't know if we can access it now. Okay, I've seen Bashir. Let me. So Bashir, I think you should have
Yes,
it now.
I've received it now. Yes,
Okay.
sir. Thank you. So, also it should be in your box any second so that you'll assist in sharing. Thank you.
So while we wait for that to be shared, I think. So I will be speaking to us generally today. My outlines will include the overview, what is the context with which as engineers should be looking at flow assurance, more importantly as Nigerians engineers. Then I'll go on to speak on what is flow assurance per se. Then from there I'll go to just to give us brief, which we're all familiar with, information gaining, the operating environment we're dealing with. Then we move on to what are major flow assurance challenges. From there, we looked at the design strategy for flow assurance. Have it speak a bit more, if time permits, on digital and modern flow assurance technologies. Or have me talk that just as the last round. But more importantly, I will speak more on the case study, the Nigerian deep water feeds. What are the flow assurance challenges, and what are the remedies that have been employed, and is there any other solutions that we could offer to get the crude out of the ground? So then we make our recommendations, and that will be the end of the lecture. So I don't know if my slide will come up now so that I can start. So if you can hear me, Ose.
Sir, yeah, I can hear you, but I'm still waiting to receive it. If you could proceed, and once I get it, I'll pull it up.
Okay, no problem. Let me just go on. So as I was saying initially, that Nigeria wants to achieve between 2.4 3 million barrel per day. That's the production target they wish to achieve. But we've been playing around 1.5. Sometimes we fall beneath, sometimes a little bit overboard. And one of the major challenges is that we have problems in our onshore facilities or platforms. Problem with vandalisms. The assets securities are not that strong. The production systems are not stable. So Nigeria, currently the strategy is to look away into deep water development, where you have reduced vandalisms, you have stronger asset security, you have stable production systems. So as we speak currently, we've heard about the news that companies like ExxonMobil, the Shell, and so on and so forth were disinvesting from Nigeria. But predominantly, we see all of them coming back one by one and investing hugely in deep waters feeds. For example, for Ulsan feeds, deep water feeds, recently ExxonMobil wants to develop, add to the already existing subsea wells. Currently, we have about 34 subsea wells at the Ulsan deep waters feeds. They're about to add more to that well, rejig the operating systems so that it can bring forth more production from these brown feeds. So they are spending about $1.5 billion in investments. Also in Owowo, ExxonMobil is saying that by they will be able to reach the final investment decision as early as 2027, where they will be able to, they are projecting about 7 to 8 billion final investment decision by 2027. So they want to invest on this. They said there's about a billion barrel developed resources within that Owowo feeds. EHA feed, currently they're extending the production sharing contracts in EHA feeds to 2042. So a lot is going on in the deep waters operation currently. As a matter of fact, my slide is about 1 week old. Day before yesterday, I heard ExxonMobil speaking, saying that they are ready to put about $20 billion in what's it called, in Bonga Southwest feeds, where they are expecting to be able to get about 150,000 barrels per day and about 140 million standard cubic feet of gas every day. So a lot is going on in our deep water operations, which is a strategy to be able to rev up productions in Nigeria. So this will lead us to what we call flow assurance. With deep water operations comes the most critical technical and economic risks in deep water operation is what is called flow assurance. And this combines a lot of factors. The fact that you are operating in the water body, the ultra deep water conditions, whether to the FPSO or to your platform. And that also requires long tiebacks of pipelines and risers and subseas and subsea wells and manifolds back to the platform or the FPSO being engaged. We also have problem with temperature and pressure variations. Your crude oil comes from the reservoir at maybe about 80 degrees centigrade, and the pipelines under subseas have the temperature that ranges between 3 degrees centigrade to about 5 degrees Celsius now. So immediately your crude that is 80 degrees centigrade, low temperature, they begin to lose out, whether through conduction and convection, the heat with them. And when they lose their health, there are big challenges, as we see later in this study. Begin to see the issue of wax precipitations, asphaltenes, depositions within the school, especially for Nigeria that has between about 40 to 50% paraffinic fluids. So these are some of the challenges that comes with flow assurance. Then also we are talking about deep waters, as we soon see. I don't know, is my slide ready or not? Sorry. Okay, my slide is ready. Thank you. So as we soon see also, some of these we're talking about between 500 meter to 300 meter deep waters body. So interventions are limited. Access to maybe well interventions and all that are very, very difficult. So in setting up deep waters operation, you have to consider first what is called front-end engineering design. This front engineering design, this is the detailed pre-construction engineering that define how exactly the project needs to be executed. This must come between your conceptual details to engineering, procurement, or construction. As a matter of fact, at this point, between 70 to 80% of the final FID, that is final investment decision, must have been made. So to develop this oil field, you need to set in place beforehand, how are we going to produce it? What provisions are we making for wax depositions? What are we making for hydrate formations? What are we making for well interventions? So it starts from that period. So you need an integrated solutions that are planned beforehand before you move to deep waters. You don't just start in the middle. It will cost money. It will lose productions and so on and so forth. So let's see what is flow assurance per se. Can we go to the next slide? Can we go to the next slide? Okay, good. Thank you. Flow assurance is defined as the design and operational strategies that is required to ensure uninterrupted hydrocarbon flow from reservoir to processing facilities, whether that is your platform, whether that is your FPSO. You want to make sure that the crude that is leaving the reservoir gets to the production platform. Don't forget, I told you that there's a long tiebacks, long distance, about 3 kilometers, sometimes about half a kilometers, running back to the production platform or the FPSO in the deep sea. So, sorry, 1 minute. So what do we have? We need a flow assurance designs that covers hydrate formation, wax deposition, asphaltene precipitations, scaled formation, slugging, which we will see very soon, sand production, emulsion formation, and corrosion. I just highlight a few of these as we go on in this presentation. So let's go to the next slide, please. So next slide, please. Okay, good. So we are talking about Gulf of Guinea currently. The key characteristics of this Gulf of Guinea involve water depth, as I've said, between 500 meters to 3,000 meters. That is very deep water. The seabed temperature from 3 to 5 degrees Celsius. And we have long subsea tiebacks, so we can have about 20 kilometer. Yeah, 20 kilometer to about 120 kilometer tiebacks. So I was talking about depth the other time. So our riser could be about 3 kilometer high, while the subsea tiebacks could be between 20 kilometer to 120 kilometer. That is essentially long distance. So the temperature that comes into the wellhead before it gets to the plates or before it gets to your processing platform the temperature is gone. Then you fall into this situation whereby hydrates could form, was could be deposited, asphaltene could be precipitated. Then there are some other, a whole lot of other situations, slugging could come in. So as I've said, we have limited intervention within this Gulf of Guinea. So we in Niger Delta, we have typical within that Gulf of Guinea. Some of the feeds we have is that Bonga feeds, Agbami feed, Ejina feed, Aku feeds, Air feed, those some feeds. These are familiar feeds that we all have, and these are deep waters. Some of them are brown feeds. Some of them we are opening them up as we currently have the Bonga Southwest feed that I told you just now. ExxonMobil is proposing to invest about $20 billion in that regards. Let's move to the next slide, please. Okay. Now, one of the first major challenges that we have with deep water operation, hydrate formation. You can see, as you can see over there, I can't use my pointer, I'm not the host. You can see a plug, like a block of ice in that picture. That is hydrates. This can form when your pipelines, your subsea pipelines, multi-phase fluids that's flowing within it, fall within the phase or within the situation that favors the deposition of hydrates, form a plug and block the entire pipelines. So this is one of the major challenges we face with major flow assurance challenges. Deep water operations. You see, for hydrate to form, there are situations that help accomplish that. The first one is that the pressure must be high. Good, the well pressure is high, yeah, and you can begin to see a little bit of reduction within the pipeline as it flows from the reservoir, yes, but the pressure must be high. The temperature must be low. And also, there must be water, the presence of water. So if you look at the shaft, the phase diagram that I put in that place, you see the inlet condition. We have certain pressure. I wish I can actually highlight as I'm speaking. We have certain pressure at the inlet condition. That could be our wellhead as well. We have certain temperature. At that point of inlet, the pressure is relatively high. The temperature is also high. So that is not necessarily, it's not favorable for hydrate formation. But as I said, as you continue to pump your fluids through the pipelines, through a distance of about 20 kilometers or 120 kilometers, it begins to lose pressure a bit, but more importantly, lose temperature as the heat flows from the crude oil to the ambient, to the environment, which is water body. And as that happens, the pressure is continue to reduce and the temperature continue to reduce. Then you'll find yourself within the space, the hydrate formation envelopes, where you have multi-phase kind of fluids. You have here you have water, you have the crude oil, and you see the dew point beneath at 0% dew point. You see the bubble point beneath. The dew point, that is the first molecules of liquid being condensed into the effluent. Then gradually, as it continues to increase, we have about 40% inclusions of liquid water, maybe formation water. Formation water being produced along with the crude oil. And also here we have gas also being present. So at this condition, you are operating within the condition that is favorable for hydrate formation, which will happen if, I'm not the host. So can this person stop sharing, or can I share my, this will stop the screen. Okay, yes. So, okay, let me now start. Let me share my screen. Thank you. So, the current slide. Okay. So thank you so much. So I think right here, let me use the Pontal option. So I believe you can see my screen. Please, somebody can unmute and say yes, if that's true.
Yes, I can see your screen, sir.
Okay, thank you. So as you begin to produce from the wellhead, and you are sending your fluid into the pipelines at the subsea conditions, you begin to lose temperature gradually. And before you get to the platform, the temperature has dropped remarkably. And look at where it drops. This envelope within this place provide the multi-phase conditions that is needed to produce hydrates. You need gas molecule, hydrocarbon gas molecules, for example, methane, butane, you need propane, you need isobutane, you need the presence of those gas molecules being present. You also need water. Here, the water could have condensed from the dew point, begin to condense. I think we have about 40% liquid phase and maybe 60% liquid phase. See, this envelope here is so favorable for hydrate formation. And that will lead to us having something like this that will block the entire cross section of the pipeline. Then production stops, money stops at that point. So we have different kind of, so I said gas added crystalline structures. You must have water molecules, which will form the lattice framework that will trap the hydrocarbons molecules, the gaseous molecules, and form a stabilized structure like ice. So you can have structure 1, structure 2, structure H, or depending on the kind of gases that the molecule are trapping. But in this regard, the structure does not really contribute to anything as such. But something very important, when the water lattice framework trap gases like isobutane, propane, which are heavier than methane and co, what happens is that it forms an hydrate formation that has high melting points. So to get them off the pipelines is difficult. And so the condition to make sure, and also this can form at even high temperature. Yes, high temperature. So at the condition closer to what you have at the wellhead, you can still have hydrate formation. When you have the water lattice formation trapping the heavier hydrocarbon gas molecules like isobutane, like propane, and so on and so forth. So at high temperature and high pressure, you can still have hydrate formation. So that's the major difference between all these structures. Other than that, the other one, the structure 1, only forms at the condition where you have low temperature and relatively high pressure. So what do we do? How do we get rid of this? Although we speak more about it later, but the first thing you can do is to play around the operating conditions. What are our operating conditions? The flow rate, yes. But more importantly, the pressure, yes. The temperature of the fluid that is coming from the reservoir. And that will require that you insulate your pipelines. And a lot of methods we see as we go on, whether pipe in pipe, and so on and so forth. You can use aerogel, you can use mineral oil, you can use wood oil, you can use some, what is it called, PPF, some foams, some chemical foams to insulate your pipelines so that it doesn't lose its temperature. Or you can actually do well-planned depressurization of the pipeline so that it doesn't stay at essentially high pressure. Okay, so you can do a planned depressurization of the pipelines. So we'll talk about that shortly. But other thing you can do to deal with hydrate formation is to entirely move the hydrate equilibrium curve. This is the hydrate equilibrium curve from the hydrate zone, the region where the hydrate could form, which are this one. So you want to push the hydrate, this curve, the hydrate stabilization curve, or hydrate equilibrium curve, you want to push it to the right. By what do we do? By having inhibitors. So we have thermodynamic inhibitors that involve methanol, methylene ethyl glycol, and so on and so forth, to actually reduce the water activity. This literally push to the right the hydrate formation curve. So your fluids within the pipeline will not form anhydrates that we have here. The other kind of inhibitors that we have is low dosage inhibitors, hydrate inhibitors that they normally had. What this one does, example of this one is kinetic inhibitors. The other one that's called anti-agglomerants. Yes, this one does not affect the water activity, but what it helps to do is to delay the formation of the hydrates, especially imagine during shutdown. You don't want during shutdown, your fluid within the pipeline cool down rapidly and eventually will lead to hydrate, provide the condition that favor hydrate formation. So let's go on to the other slide so we don't waste so much time here. So for example, this is our wellhead condition. As you are producing, as your fluid is coming from the wellhead, going towards this one, the pressure is relatively not too low, but it's still high, yeah. Whereas the temperature is strategically definitely coming down. If you continue to do that, what we have is that you will fall within these hydrate rig zones where the fluid within the pipeline will form anhydrates. So what you want to do is to offer an operating condition that return this back to these favorable conditions where the temperature is still high and the pressure is low. So that's what you want to do. So sometimes, as I mentioned earlier on, what people do is to add inhibitors. So you also, because the inhibitors are expensive, like the MEG, the methylethylene glycol inhibitors, is highly viscous. It can also, if you don't know how to apply it effectively, it can also begin to cause, make the fluid become more sluggish. So you don't have to apply so much. You just want to get your hydrate equilibrium curve to a safe and optimized region, the green line over there. Or if you have so much inhibitors, what you will have is that you will have the hydrate formation curve that is far to the left, which is over inhibited. So this is over inhibited condition. This is what's it called? This is low safety margin, and this is under inhibited conditions. So in Niger Delta crude, we also have the problem of wax deposition. So in Nigerian crude is highly paraffinic, where we have about 30 to 45% of our crude having that composition of hydrocarbons. So there's a great challenge about wax depositions. So it can block major operational issues, include pipeline blockage. It can decline production rates because you just fill up the entire pipe at the cross section of the pipelines, as we soon see. Then it costs a lot to be able to carry out remediations and maintenance once this wax deposition have been formed. So we have a number of factors that leads to this. As we said, temperature, that's most dominant. You want to avoid the wax appearance temperature. Then two, pressure reduction. As the pressure reduces from the reservoir conditions or from the wellhead conditions and your fluid continue to flow, what will happen when the pressure reduces is that the gas, hydrocarbon, the gaseous content within the effluent, within the production fluids that is coming out, they begin to get liberated. So as the gas is liberated, the fluid become more viscous, which becomes a favorable conditions for wax deposition to set in. Then you have crude composition, I said, which this paraffinic nature of the crude has high degree of tendency for a crude oil to form wax. Then the flow rate has to deal with if the flow rate is low, then you're operating within the condition that is called laminar operation system. That means the inertial force is lower than the viscous force. So when the viscous force is larger than the inertial force, the inertial forces are governed by the velocities, so on and so forth, while the viscous forces are governed by the viscosity of the fluids. So when your flow rate is low, you have a laminar flow conditions that also favors the conditions that makes the wax to settle. But when your flow rate is high, you are having what is called turbulent regime, where the inertial forces, that is the velocity, the shearing, and so on and so forth, is higher than the inertial force. So at that point, you have high shearing rates. So as soon as the wax crystals are being formed, the forces can actually shear them, remove them, though we now distribute them across the pipeline. So that's about flow rate. Then pipe wall roughness. The internal surface of the pipeline will also help stabilize the nucleations of the wax molecules, and so on and so forth. And pressure reduction can also, the gas evolution is as I described under the pressure reduction. Wettability, if your pipeline is water wet, what that implies is that the hydrocarbons, which also is wax, will not be the one to have the final touch with the surface of the pipeline. But if your the pipeline is oil wet, that means oil will displace water to have the first contact with the pipeline. So the closest fluid to the internal face of the pipeline will be oil, and that allows the wax molecule to nucleate, crystallize, and then form a hardened structure, especially if it is microcrystalline wax deposition. In that regard, we have microcrystalline wax depositions, and we have micro, as we soon see. So paraffin structures that actually leads to this wax deposition. We have what is called straight chain. Those are normal paraffin. And we have the branch chain and cycloparaffin chains, that is naphthalene, that forms this wax deposition. You can see here, 1 minute. As you can see here, we have the straight chain paraffins, which is responsible for the formation of microcrystalline wax deposition. Why is that? They are able to form tightly and neatly a lamellar structure that is very, very difficult to break, have high melting points, unlike the amorphous wax deposition, that is microcrystalline, which are formed by the cycloparaffins and branch chain. This one are softer, they are thicker, they don't have high, they are not strong, they can easily be shared by increase in velocity of the fluid constituents within the pipeline. But once the straight chain microcrystalline wax molecule are formed, they are very, very difficult to remove. That will be that about the contribution of the chain structures of those wax molecules. So here we have the wax deposited within the pipeline. These are wax deposited around the surface area. The cross-section area is reduced. Look at the little space left for crude oil to pass through. Definitely there will be declining production with this. And also look at the viscosity. So it will require more pumping force to be able to pump the crude to the platform or the processing facilities once the wax begin to fall. There's even another situation, especially during shutting or shutdown, that if the temperature of the crude oil continue to reduce stay below the wax appearance temperature for too long, you form a gelations kind of fluids that is very difficult to move. As a matter of fact, you cannot move it until you overcome a threshold shear stress that must be applied, which sometimes will be more than the normal operating pumps, before the flow can proceed. Once the wax cause the crude oil to gel, as we have here. And this diagram is talking about this is the pressure. At this point, you are the bubble point. Once the high light ends, like propane, butane, all those gaseous composition of the crude oil or hydrocarbon are escaping at the bubble point, what we have here is that the wax appearance temperature will continue to increase. So that means initially, if your crude oil, your pipelines or the crude oil concentrated within the pipeline cools to maybe 20 degrees, that is when you begin to have wax. Whilst the hydrocarbon, gaseous hydrocarbon component like propane and butane, the light ends one, begin to escape at bubble point, you can see that the wax appearance temperature is going up. So you can be at 30 and your crude, and wax begin to deposit within your pipeline. So you want to also maintain, you don't want to go below bubble point as you even depressurize, so that wax problem, because you are running from hydrates, you don't want to maintain, lower the pressure so much that it cross the bubble points. So these are give and takes that goes on with planning and flow assurance within the deep waters operation. So like I said before, once your wax causes your crude to gel up, you need what is called breakaway yield strength, which people are dealing with multi-phase fluids, which is called Birmingham model, to overcome the yield strength before you can have a reasonable flow again. Sometimes when these wax fluids get deposited or our fluid become dilated, what happens is that we have what is called thesotropic nature of fluids, whereby increase in shear rates, definitely leads to reduction in viscosity once we overcome the yeast strength. So you don't want your crude oil to gel within the pipeline, because it costs more, it takes more effort to be able to get the fluid flowing again. And as I said initially, we have two main wax deposition mechanisms through molecular diffusions and shear dispersion. Molecular diffusion is what we have when we have laminar flow. As I said before, we have laminar flow when the viscous force is greater than the inertial force. So they are dominated by molecular diffusions driven by temperature gradients. I think I need to slow down there. What I'm saying here is that when you have your pipelines and the fluids are flowing gently, easily, what the wax deposition mechanism, what wax deposition mechanism is called molecular diffusion. Because what you will have, number one, the surface, the internal surface of the pipeline is cold, right? More cold than the fluids. So at the center of the fluid, at the center of the pipeline, you have the highest temperature. Close to the wall of the pipeline, you have the lowest temperature. So you have what is called temperature gradients. Then at high temperature, normally that there will be more dissolution of the wax molecule within the crude. So the highest point at laminar flow condition, where we have the wax dissolution, is at the center of the fluid. And close to the wall, where the temperature is beginning to approach the temperature of the pipelines, you have the lowest dissolution of the wax. So because of the temperature gradient, you will have what is called concentration gradient. Concentration being higher at the middle and lowest close to the pipeline. So there will also be what we call, so for osmosis, this is osmosis now, from the, that is moving from the region of highest concentration to the region of lower concentration. So the wax molecule begin to migrate towards the pipelines and eventually deposit on it. So the shear force in this regard is negligible because the inertial force is lower. In turbulent multi-phase flow, you have is basically by shear dispersion, and this is caused by velocity gradient. If you have your pipeline, I think also need to slow down here. At the middle, you have the maximum velocity at the middle. And at the wall, you have the lowest velocity of the fluids. So you have something like this. As with this pipeline, you have something like this. The reason is that the highest frictional force is close to the wall, the surface of the wall, that is resisting the motion of the fluid. So you have the fluid going very fast in the middle and going very low at the wall. So this causes a velocity gradient, and therefore there's higher shearing at the middle of the pipeline than also the wall. So because it's being shared in the middle, the shear dispersion will, number one, disperse the wax molecule across the pipeline, but also pushes it also to the wall. But because of high flow velocity or high flow rate in the shear dispersion mechanisms, it could remove the wax molecules deposited on the wall that are not firmly deposited. And what these guys are doing there is some of the things that we do to remediate wax deposition. This is pigging. They are sending that to, we'll go through all the pipe and push out all the deposited wax that are already settling across the intersurface of the pipeline. So in short, this is the breakaway yield stress that I was talking about the other time. You can calculate it. This can be modeled. This is the pipe diameter. This is the pressure. This is the differential pressure. This is the length of the pipe. And you can calculate the needed breakaway yield stress to mobilize already gelated crude oil within your pipeline. So you can just, that can use to be calculated to calculate the shear stress, the threshold shear stress that you need. So let's talk more about this diagram. Let's say we have a pipeline that ordinarily the pipeline has overall its transfer coefficients of 10 watts per meter square degree centigrade. Then as our crude oil flow from the wellhead across this distance, 2,000 meters, 4,000 meters, 6,000 meters, 4,000 meters, and so on. And the red line here is the wax appearance temperature. This is the temperature where the wax molecule begins to nucleate, crystallize, and get deposits. So as your fluids continue to flow, by the time they get to 2,000, the temperature of your fluid is already getting close to 60, 50. Then you have crossed the wax appearance temperature. Then wax has begun to form within the pipeline. So what you want to do is to look for a coating, an insulating material that can prevent the heat loss through conduction and conduction and convection from the crude, so that your temperature, the rate at which the fluid is losing their temperature, is reduced to this. So it's only at 10,000 meters that wax begin to appear. So this one that even have 2 watts per square meter degree centigrade, it's not good enough, because before we get to 12,000 meters, assuming now, which is our final destination or processing plants or platform or FPSO, wax has already formed. So we want to look for insulating materials, whether it's aerogel, whether it's mineral oil, whether it's PPF, whether it's PUF, different kind of material that we can use that has overall heat transfer coefficient of 0.8. And once we use that kind of material, it will preserve the heat of the fluid to get low, so that our fluid, the temperature, the operating conditions, will never reach that, will not get to that point where you begin to have wax deposition. This is the whole sense behind flow assurance engineering. This is what they do.
Hello, sir. Sorry to interrupt, just to help keep track on time, because I'm sure you can't see the message I must have sent.
Oh, okay. So how many more minutes do I have? Let's go ahead.
11 at this point.
Okay, let me just run through.
Thank you, sir.
Some other challenges that we also have is we have slugging, and there are different kinds of slugging. We have stratified slugging, stratified wavy flow, the plug flow. Slugging happens when you begin to have within your pipeline the intermittent flow of liquid plugs as well as gas pockets flowing together. This can cause serious problem within a pipeline. There are different types of flogging, mechanisms of slug. We have hydrodynamic, we have terrain, we have severe riser slugging. Let me just speak more on this severe riser slugging because of time. You have your riser connecting from your pipelines to the FPSO or your platform. And what will happen when you have the grove length of liquids and pockets of gas is that when it gets here, the reason why this happens is because gas travel at higher velocity. Gas that being produced within your pipeline travel at higher velocity than water, which is expected, or than crude oil. So what will happen in this regard is that when the crude oil gets to the base of the riser, it settles there, then it blocks the pathway of the gas. So as it settles there, gradually there's a large liquid slug here, but gas starts to build up behind that slug. Then at some point, the pressure of the gas that is built up will push off suddenly the crude into the weather separators and all those things, which you don't want. Number one, it causes unstable production. It causes your separator can be overrun, can be flooded. So you cannot specifically pick the liquid from the gas or from the water, from the oil. Then it comes with vibration. It comes with structural stress and facility loading that can damage the top facilities in our flow assurance. So you don't want this kind of production. So, but you do have it if you cannot predict this kind of flows that also happen within our facilities. The slide will be available, and we'll go through some of all these things. So what do we do now? Let me slow down a little bit here, just 1 minute to explain this. Let's assume this is our crude oil, this is our pipeline, this is our insulators, this is another pipe. This is a pipe and pipe system. Your fluid, the temperature is highest at this point. Then via convection, the fluid is losing its heat, is moving from this water to this pipeline material. Then via conduction, the heat is also flowing through this material to the insulator. Then via conduction as well, is moving from this insulator material to the outer pipe. Then via conduction, the heat is flowing from this pipeline then to the ambient, which is seawater. And you can see here, you can model the flow, the heat flow for each of these elements, and eventually get the overall heat flow rate across this design. So you want to manage heat transfer. So you want to be sure the kind of property that will get you the amount of heat flow rate that you need. You can easily model this. This is also pipe in pipe situation where we have this production pipeline. Hot water is being supplied through some pipeline within this one. This is an insulation. This gas injection for interventions. These are control and so on and so forth. This for impetus injections and so on. So these are some of the design laid within the seabed. You can also do what is called direct electric heat, where you use alternating current and use your pipeline as the conductor. And because there's a heat of resistance, it will be generating heat, and that heat will be warming up the fluid composition within pipeline. And you send a return cable to this back cable into the platform. So you can, there's a complete circuit of your pipeline. And this will help you to warm up your fluid, especially during shorting. These are also some other methods. Some other method that we also use is we have slug casher for the slug flow that I was explaining the other time. We have majorly two types. You can use finger type slug casher, and there's also the vessel type slug casher that helps you. So it doesn't allow all those vibration and all that. Also, please, you can let me know when my time is 5 minutes more, so that you can unmute and speak when I get to that
Yes,
point.
we are at the 5 minute mark now, sir.
Okay. So
All right, sir.
we also have this type of vessel types like Kasha and so on and so on. So there are a number of models that we can use to predict the empirical formulas that we can use to predict our slot growth. I mean, our slots, the length of our slots here. This is modeling the mean slot length, so we can know the capacity of slot caches we need to put in place based on the conditions of our operations, and so on and so forth. Also, there's a model for the slide will be available to calculate water hold-ups. And water hold-up is defined as the fraction of a pipe or of a flow system occupied by liquid as opposed to gas in any pipeline flow system. So the models are also available for discuss, and there's 18 methods for modeling liquid hold-up. Because this method assumes what is called no-slip conditions. It means that it's saying that the velocity of the gas and velocity of the liquid are the same within the pipeline, which is not a reality. So this method is better to predict liquid hold-up. So we have a few number of feeds in Nigeria. We have what is called a Bonga feed. It commenced production in Q4 2005, not 2025. So some of the documented flow assurance issues that we have in that regard is high pressure, low seabed temperature, severe slugging, wax depositions, and so on and so forth. And conditions that were around this because the water depth is about 1,000 meters deep, and the subsea tieback long about 2 to 10 kilometers. This is not even that long. We have long multi-phase flow lines, cooling, terrain slugging, and all that. And the number of engineering solutions that are available are also listed. We also have a half feeds, documented flow assurance issues as hydrates, asphalting deposition, emission effects, what is responsible, complex reservoir fluid, deep water cooling and pressure drop, and long flow paths, and long multi-phase flow lines. These are some of the things. Engineering solutions that are currently used, management of hydrates, asphalting inhibitors, heated flow lines in critical section, and so on and so forth. So Orga is one of the software we can use to also manage some of these deep waters facilities. The software that I hope that SP can facilitate the cooperation between the industry and the training institute like Petroleum, where we can get student license to use this to train them as well. We can get student use version so that we can use it to train students, because the license is expensive. And we have wax deposition issues in the Agbami hydrates. The conditions are listed there. We have ACPO, the conditions are also listed there. We have Egina, the conditions are listed there. The slide will be available. I'm running because of time. So my recommendation for the Gulf of Guinea, we have to have early flow assurance integration. We must incorporate flow assurance consideration early in field development planning. It is not in the middle where we begin to plan for flow assurance. It must be feed into the feed. That is the early engineering designs that is needed, so that we don't have frequent intervention, which are very difficult to do. Digital monitoring adoptions, that's digital twins, artificial intelligence, deploy artificial intelligence, and so on and so forth, to be adopted. Where we emphasize more is the next two, the local capacity development. Nigeria is moving towards what is called deep water operations. We need to provide local skills, manpower, local content that will be able to man this. So places like Petroleum Training is where I proudly work for, is ready to collaborate with facilitating short courses for people who are willing. We can partner with other people in the countries who can help us to readily make some of these softwares available and train, develop manpower so that we can function effectively within this new era of deep water operations. Then we should have regional flow assurance research. The FUPRE, the Petroleum Training Institute, can partner together with the oil and gas, which SP, I believe, can facilitate to promote research and development collaboration. We also need to improve subsea intervention planning, clear well architectures, correct data of our facilities, instead of reactive intervention to predictive monitoring. These are some of the things we need to imbibe if we want to have a successful deep waters operations. So I will stop here. Thank you for your attention. Sorry, I'm very fast. I just want to make sure I finish within the timeline. Thank you.
Thank you very much, sir. I know that was a lot to unpack in such a short time, but we're very grateful. Thank you very much, sir. I don't know if any of the section directors on call would like to say something for a few seconds before we proceed.
Okay. Yeah. Good evening, Engineer Timothy. Good evening. Thank you so much. First, I want to apologize. I came in a bit late. I had an urgent meeting. Our new CEO that came on board, and we just needed to onboard him from NMDPRA. So it was so urgent. So, but I had to come in here. But with the little I heard, that it was so impactful. So much. I think I have missed a lot. I've missed a lot, but particularly for the fact that some of us who are here, with what we've heard, even with the little I've heard, it's a great one. Understanding the challenges, particularly with flow assurance, being able to model out solutions that will allow us to predict and control and manage. It's a very good one. I think it's very key, not just only in flow, not only, but every aspect of our life. Understanding the challenges, using histories, statistics, and practical experience of what we see around us, and be able to develop models that can help us to begin to say, okay, within the next operations, activities, and all that, you can begin to monitor and predict and ensure that we optimize our processes. Thank you very much, sir. Thank you very much for honoring us, and I really want to appreciate you for this presentation and lecture. Thank you.
Thank you so much, sir. Thank you, sir. I'm very grateful.
All right, thank you very much, sir. Thank you very much for that, sir. Now we'll be moving on to the Q&A session. But before that, I'd just like to reiterate some of the key takeaways. We've looked at the flow assurance challenges and strategies and a few recommendations, and the slides will be made available to everyone. But if anyone would like to, if there's any questions at this point, please just indicate by raise of hand, and we'll proceed to have those or to entertain those questions. Or you could leave it in the chat box and I would read it out. Should we take the no show of hands as the fact that we all understood the presentation completely?
Yes, Ose, thank you. It
All right,
was
then,
elaborate and intensive. Yeah.
right. Okay, that's great. So we'll be moving on to the next item on the agenda, which is the photograph. At this point, I'd like to implore everyone to please turn on their cameras so that we can have the photograph, the group photograph. Okay. We will need more people to turn on their cameras, please. Okay. Great. There's still a number of people. I might have to start calling names just in case you're not aware that your camera is still turned off. Engineer Kizito, Mr. Lucky, Engineer Christian, Bethel. Okay. So I'll be taking the screenshot now, just so we have the photograph. Okay. Just one more, just to confirm, please. Okay, great. Okay, thank you very much, everyone. Right. Okay, so we're gradually coming to the end of today's technical lecture. At this point, I'd like to call on Engineer Elvis Duruji, Programs Chair, for the vote of thanks and closing remarks.
Okay, once more, let me continue from where I stopped. I want to thank, on behalf of the section chair and the directors of the SP Warri, section 104. I want to appreciate Engineer Timothy. Thank you so much for honoring this month's technical lecture. And not just only honoring it, you've been able to impact on the topic. We really appreciate you. And I want to believe that every one of us here will agree with me that today's lecture is highly relevant in what we do. So I want to thank all the directors here present. I want to thank the YP and the students and all the members. We want to appreciate you. Let's continue to work. Let's continue to be present because the world is dynamic. Every day things are changing. It is such a platform that SPE provide that helps us to keep at pace, that help us to keep up to date. There are a lot of things you might not learn from school. You might not learn even in your own workplace. So, but when we come to forums like this, we cross-fertilize ideas, we keep improving on what we do. So thank you very much, everyone, for coming. And I want to look forward to next month, TL. And use this opportunity again to tell you our ATS is coming up next week, 30th of May, from 28, 29 to 30th is going to be awesome. Please make sure you get involved and let us begin to prepare for such a wonderful symposium. Thank you all and have a great day. Bye.
Thank you very much, Programs Chair. And with that, we've come to the end of our technical lecture for me. Thank you very much for everyone who was in attendance. Thank you to our guest speaker. And as our chair has said, till next month, see you.
Thank you very much.
Thank you very much.
Thank you.
Thank you all.
Thank you.
Thank you.
Bye.